All right, recording is rolling. It is Monday, December 4. I have Kahoot lined up for you guys, conceptual questions. A lot of you guys hopped on already before I hit record. Right? If you want to follow along with the questions, they're printed on the opposite side of these thumbnail notes that I gave you guys about a week ago. So it's these questions right here. Right? If you want a printed version. My plan is Tuesday, do more textbook puzzles with you guys. We got to start on those last week, but keep doing those. I have a rotational inertial lined up for this week. Oh, Wednesday, there's no resiliency lessons. There's a bunch of testing going on. Now, I did check the Excel files. I didn't see any of your names on it, so I don't think you were testing. It's wrong, but anyway. So, a bunch of testing going on those. Now, back on Friday, there were a bunch of students absent. So if you were absent, you can check the recording, see everything we did. I just love this bicycle wheel, this low friction bicycle wheel, right? I was showing a conservation of angular momentum with that. If you give it a spin, then it'll look like it's levitating, all kind of fun stuff. So still have that around a couple days. If you missed that, get your hands on that if you get a good opportunity. All right, with that, let's switch over to this Kahoot right here. Kahoot. All right, you guys are hopped on, ready to go. Start the thing, rotational motion. Which has greater linear speed, a horse near the outside of a merry-go-round or one near the inside? Ooh, all right. Outside horse. So the question is about linear speed, right? Linear speed. That's the original way you guys learned about speed. Let me give you guys a graphic to look at. I guess this. Okay. I think this one's hanging in my room right now. Let's see, it's here. So if you had a turntable, you guys remember the turntable, right? You guys remember like these three Roosevelts on this turntable, right? So if you give this turntable spin, right? Well, you can see the animation how it's playing out. See how the guy in the middle has like zero linear speed. He's not really moving anywhere. Right? If you stand off to the side of this merry-go-round and you point a radar gun at this middle guy, it's always going to read 0 meters per second. It doesn't matter how fast it's spinning. Right? It's zero. Right? But then the further out you go, the faster they go. Right? Like you guys see this guy on the outside covers a huge distance in the same interval of time that this guy covers a little distance, this guy covers no distance. Right? The math connection is this one right here. Here's linear speed. That's what the question was about. Right? And then as a function of radial side. So the further out you are, like if you're 3 times far out, you're going 3 times as fast. Right? Now, what about angular speed? I think that's the next question lined up. Right? Angular speed. Isn't that omega, right? Which is like turns per time, radians per second. Guys, do all these 3 Roosevelts have the same turns per time? Like, would they make one revolution in the same time interval? I think they would, right? Right. So I think they have the same radians per second, but different meters per second. Right, all right. I think that's the next question. So see if that pops up. All right, we got Finn and Jake the dog with some points. Which has greater angular speed, a horse near the outside or inside of a merry-go-round? One winner. All right. I'm gonna find the Paul Hewitt version of this. Where's okay? Hold on. Gotta minimize a bunch of windows. Okay, and fine, get out of the way here. I will find. I know I have it. I know I have Paul Hewitt's. Okay, come on, open this folder. All right, we're gonna see Paul Hewitt explain this one. Yay, that's physics. Oh yeah. There's the answers to the first two questions right there. All right. All right, let's see how we're doing on points. Ooh, Finn, 1776. More points. Whirl a tin can on the end of a string. The string suddenly breaks. The can will. Yeah, there you go. Fly off tangent to its circular path. I think it was a really similar question back in the gravitation days. Like if you turn off the gravity from the sun, what would the plant do? And it was the same answer, right? It would just fly off like in a straight line path, like tangent to the motion it's already going, right? Okay. Okay, so yeah, if you pick the red one, that's kind of like the intuitive but wrong answer that a lot of people think like before they take physics, right? Think, oh, it feels like you're being pulled straight away, right? But no. Actually, let me draw that out, right? Show you guys the difference between the red and the green on a picture. Okay. So, please, here. Okay. So we're like helicopter view looking straight down. I see a tin can on a string, and zoom, 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 and suddenly you cut the string right there. Okay. The correct answer, which most of you guys got, is that the can is going to fly off tangent to its motion. That's like that direction right there. Call it V for velocity, right? It's going to fly off that way. Right. All right. That is the correct answer. Most of you guys got that. I need the graphic for that one. Go. All right. Lots of points. All right. Points. As the rotational speed of a space habitat increases, right, think one of these O'Neill cylinders, right, the apparent weight of the people inside. Ooh, also went real fast. Okay. Increases, decreases. Let's see, I'm trying to dig up this poster from back in the day where, okay, I know it's somewhere back here. I covered this a few weeks ago. Okay, I will find this. I found it. There you guys a short time on that one too. Okay, that's this one right here. You guys remember this? This out in space, it's spinning, right? There's no real gravity around. Right? But if this thing's big enough and it's spinning, then if you're walking around the inside, it might be hard to tell, right? But if you climb this ladder, ooh, you'll get all different experiences. You guys remember right in the center, it actually would feel weightless, like no gravity. If you were at the center of this ladder and you pushed off, you just like float off into space, right? But then as you walk down the ladder, and then you feel more and more gravity. It's artificial, right? Okay. And then yeah, you can walk around on the inside surface here, right? In fact, that artificial gravity is directly proportional to your radial distance from the center. So if you start at the center, you climb like some distance down the ladder, and then you go like 3 times the distance, you would feel 3 times that acceleration. Ooh. Right. There you go. Feel heavy. 4 points. Number 5, car travels in a circle at constant speed. The net force on the car is directed toward the center of the curve. Ooh, one winner. Yeah. Okay, so this is kind of a mix of questions. Some of the later questions, like the second half of these questions, is the more recent stuff. Yeah, some of these questions are actually a review from a few weeks ago. So let's look at review from a few weeks ago. Centripetal force. You guys remember this lab with the Play-Doh canisters and the string and the PVC pipe? Right, you went around circles, right? Like what force was holding this top Play-Doh canister in a circle? Well, it was the tension of the string, and that was pulling in towards the center of the circle, which is the answer to the question. That's the direction of centripetal force. It's always towards the center of the circle. Okay. I think I recommended you guys watch a Vsauce video called Spinning, and I put the link on Google Classroom. And that one, he goes back and also does a recap of this right here. Okay. There was a similar type poster. It's a bit more, okay, like if you go down one more step over, right? What if you have a car going around a banked track, right? Now, it's still on a curved path. So this could also be that question, right? But maybe instead of friction allowing it to make the turn, maybe it's something to do with the fact that the road is banked, right? But the centripetal force still points toward the center of the circle. In this case, it's the horizontal component of the normal force is what would be, right? It's this component right here. But notice it's directed toward the center of the circle. Okay, that's going to force the car, like as it moves forward, to also make the left turn in that case. Okay. All right. Yeah, centripetal force. All right, we got Caitlin, Maya, Geo, Jake the dog, and Finn. What is the relative gravitational field along the axis of a rotating cylindrical? Oh, space apple. Hey, that's like a cylinder. Yeah, zero, zero. Okay, so let's switch back over here. You guys can see exactly that. Okay, so hey, that's what I was just saying a minute ago. Like, if this guy climbs this ladder to the very center of the ladder, which is right here, hey, that is along the axis of rotation. That's his dashed line right here, axis of rotation. So if this is spinning, then remember just a minute ago I said you would feel zero gravity at the center. If you like pushed off from the ladder at the center, you just like float off into space. That's that question, right? And then here's the math to back that up. Right? Whichever one of these you look at, if you're at zero radial distance from the center, you feel zero gravity. Well, artificial gravity, but you feel zero of it. Zero times anything is zero, right? Zero. Who got them points? Ooh, I think got Paige and Jake the dog getting the points. A wrench is slid spinning over a frictionless tabletop. Its center of gravity follows. Yeah, a regular straight line path. Okay, this connects to something we were talking about back on Friday. Okay, you guys remember I had those foam boards and we're trying to figure out what's the center mass? I said there were three different ways you could find center mass. Right? You could hang it from strings and the string would always pass through center mass. You could balance it on your finger. Or you could throw it spinning in the air. And spinning in the air, it would spin about its own center mass. Right? Now, instead if you threw it through the air, it'd follow like a projectile path right, at one point, right? But this is on a frictionless tabletop, which is like a horizontal surface, right? So it basically wants to go in a straight line. But here, draw this out so I have a picture to follow. Right, so you think about. Okay. Right, let's get a wrench going. So a wrench is just this weird shape object, right? Right. Maybe its center mass is maybe about there. Can't guess. If I was balancing it on my finger, maybe that one, right? Okay. And if it's on this huge frictionless tabletop, right? Maybe like air hockey, it's like floating, right? You give it a spin and throw it, right? So it's going to be going every which way. So it's like spinning, right? It's spinning about this point, right? If you attach an LED light, like right here, bing, then you would watch that point go like, it'll look all curly and crazy. Okay? If you attach an LED light right here at the center of mass, bing, guess what that point does? This nice straight line path. Okay, that's it. Right? Even though everything else is going all crazy curly key patterns, right? Yeah, straight line path, center mass. We follow Newton's first law of motion, law of inertia, right there. How we do on points? We got Kelly, Paige, Geo, Jake the dog, and Finn. If an object is unstable equilibrium, any displacement will. Unstable equilibrium. Yes, any motion will lower its center of gravity. Let me find my notes from last week because here we go. Right, this is notes from last week. So back over here. All right, here we go. All right, remember last week I was defining for you guys in terms of physics what is unstable or stable or neutral for that matter, right? So stable, if you give it any bump, that would have to raise its center mass, like this pyramid shape or this picture frame, right? Which it doesn't want to do, which makes it stable, right? It wants to stay. Right? But if you like try to balance a pin, right, well, that's really hard to do because any little tight vibration motion is just gonna lower its center of gravity, which you would rather do. So it's just gonna fall over. That's making it unstable. Right? And then neutral is like that ball in the middle. You go to bump, its center mass doesn't go up or down. You get neutral. All right. Center of gravity. I got Caitlin, Paige, Geo, Finn, Jake the dog. If an object is in stable equilibrium, any displacement will. Yeah, raise the center of gravity, which you would rather not do. So it's stable how it was originally. Right. Aligns with that picture I just showed you guys. I got Geo on fire, Finn and Jake the dog in the lead. Number 10, if an object is in neutral equilibrium, any displacement will. Yeah, neither raise nor lower center gravity. Okay. So let's take a look at this one more time. Boom. All right, there's pictures right there. Unstable, neutral, and stable. There you go. All right, everybody all right so far? Lots of points. A ball resting on the floor. Ooh. They got neutral equilibrium. Or we were just looking at that, right? Neutral. Here, let's see this picture again. All right. So that picture right in the middle, neutral equilibrium, because if you give it a push, like, it'll start rolling, but its center mass doesn't go up or down, so it makes it neutral. Right? Ball on the floor. Oh, and switch. All right, got Finn back to the top spot. A picture hangs on a wall from a wire passed over supporting nail is in stable equilibrium because. Yeah, there you go. Those are all true. Center of gravity is below supporting nail, right? Just like your foam boards last week. That was right. Those were stable. You can figure out that way. Any slight push will raise its center of gravity. Yep. So I was telling you guys on the notes. After any small push, it will return to its original position, right? It just wants to go back to how it was. So it's already stable. There you go. Those are all true. All the above. Torque. Okay. So you guys remember R cross F, right? Right. Okay. Torque. Right. Let's switch over here. I find my old my torque poster. Okay. We're talking about this right here. Right? You guys remember R cross F, right? So R cross F, right? Right, something like that. Okay. That's how you turn it up with a wrench, like this picture. That's how you open a door. Right? You guys remember last week? Like if the door hinges are here and the door handle is here, right? You push on the door handle, you're getting the width of the door is the radial arm of the door, right? R cross F. If you push in the middle of the door, it's harder to open the door. If you push really close to the hinges, it's nearly impossible to open the door, right? You need a huge force to get like the same turning moment, open the door, right? Do that. Right. And this whole thing with the cross product means you only multiply the perpendicular components. So if you push on some weird angle, then the parallel component doesn't add any turning moment at all. It's all the perpendicular, right? Only the perpendicular stuff, right? Sometimes it's written this way, R of sine theta. Now you have to be careful Make sure if you apply this formula, you're given the theta that aligns with this picture theta, right? If you're given the other angle, then this turns from sine into cosine, right? Okay. You guys know that? Or sine theta? Right. And then here, well, I got this switched over. Remind you guys what torque is. I'm gonna have a bunch of other posters. I just want to thinking about to find it. Oh, here we go. Right. There's this other perspective on torque. Torque equals I times alpha. So the extension is maybe if you have a string wrapped around a turntable and you give it a pull, zoom, right? Okay, so that's on R cross F. There's your torque. Okay, and it causes the turntable to speed up spinning. Right? Speed up spinning. That's like angular acceleration. Now, how much? Well, it depends on the rotational inertia of that turntable. Right? If it's really massive, maybe it's kind of slower. If it's really light, like it's made out of styrofoam, maybe like speeds up spinning really fast. Right, so that could be like a follow-up type question, right? But yeah, torque R cross F, right? Turning a wrench, opening a door, R cross F. Okay? Now a lot of you guys chose mass times velocity. Guys, what is mass times velocity? What is that? Is that momentum, right? Like momentum is mass times velocity. Okay. Force times time could be an impulse, which is like a change in momentum. So the red and the yellow kind of similar idea, same units. Okay. Mass times acceleration is a force. Yeah. Okay, so force times lever arm. There's your R cross F right there for torque. Resistance an object has to changes in its rotational motion is called rotational. Inertia, rotational inertia. Yeah, that was here. Yeah, flip my screen over. Most of you guys got that, which is great. That's this capital I. That well, okay, well, that's why I pulled this poster up, right? To remind you guys the connection, right? So torque is R cross F, RF, get speed spinning, right? But then I said, well, how much is the speed up spinning? So that's angular acceleration. Well, it depends, like, what's the rotational inertia of this turntable, right? Rotational inertia, you guys remember, has something to do with like mr squared. You guys remember, say this tightrope walker with a long pole, right? The long pole gives them a lot of rotational inertia, right? So something to do with that. Okay, different rolling objects have different. Okay, here's like a whole table of rotational inertia values, right? Okay. All right. All right, got Caitlin, Paige, Jake the dog, Geo, Finn. Which has more rotational inertia, a bicycle wheel or a solid disc? Let's say same mass, same diameter. Yeah, bicycle wheel. Okay. In fact, it has exactly twice the rotational inertia. Okay, so straight off the rotational inertia table, a single point is mr squared. A bicycle wheel, you can treat that like a ring of mass, so it's all mr squared. So, right? But a solid disc, there's more mass that's like located towards the center, so it's not as much. It ends up being half of that, right? Okay, half mr squared. All right, you guys did get there. Points. When an ice skater pulls his hands in to turn faster. Yeah, all the above is true. Okay. All right, most got that. Let me find my poster on that. That's this poster right here. Okay. So what's conserved is angular momentum. This says angular momentum initial equals angular momentum final, well, the sum of, but okay. Right. Okay. Oh, so this, before and after, it's the same. It's conserved. Right. This is kind of analogous to like a collision and the linear momentum sense. Right? And what is angular momentum? So it's I times omega, kind of analogous to mass times velocity. Right? And then when you bring your arms in, you're decreasing your rotational inertia. It's mr squared. Well, the r is going down, right? So your mass getting distributed closer to your central axis that you're spinning about. Therefore, omega is forced to increase so that this angular momentum is conserved. There you go. Right. So all of those things are going on as the dynamics of a figure skater going into a spin. All right. Huge rotating cloud of particles in space gravitates together to form a dense ball. As the cloud shrinks, it rotates how? Yeah, faster. That's the exact same principle as the ice skater, right? So ice skater brings arms in, spins faster. Hey, if there's a huge cloud of like space dust, right, and it gravitates close together, right? That's similar to the ice skater pulling their arms in, right? Angular momentum is still conserved, so yeah, for the same reason they would spin faster. Right? It was exactly in line with that poster you just saw. The ice skater. All right. Got Finn on fire. Two people sit on a balanced seesaw. When one person leans toward the center of the seesaw, that person's end will do what? Seesaw. Uh, yeah, we'll rise. We'll rise, right? I do have a seesaw poster, so I'll flash this up here. So let's say you got a couple of friends and they're balanced on a seesaw, right? So they have the same arc cross F, right? Right, 3x mg or x and 3 mg. So both the same torque, except one's clockwise and one's counterclockwise, so they're all balanced, right? Well, if one guy gets closer to the center, that's a smaller radial size. That means not as much torque, which means like not as much influence to rotate that direction, which means it's going to rotate like this, right? Or if this guy scoots in towards the center, then it would rotate like this. Yeah. So if you scoot in towards the center, your end is going to rise. If you scoot out towards the edge, your end is going to fall down. 19. To turn a stubborn screw, it's best to use a screwdriver. This is not a wrench, this is a screwdriver. Ooh, one winner, wide handle. Okay, we haven't exactly talked about this yet, but here, I'll draw a picture and you guys will see why. You want to use a wide handle screwdriver. Wide handle screwdriver. So, right, so I remember the wrench. Let me go back to the wrench, which is not what this question is. But a wrench, you would want a long handle. Right? Here's a wrench, right? So you have a long handle, call that R, and then you apply some force at this point, F. There's your R cross F. Right? Get a torque rate. That's a wrench. Let's look at a screwdriver. Screwdriver, got some screw. All right, and then here's the handle of the screwdriver right here, something like that. Right? So you wrap your hand around, right, and then you're trying to turn like that. Right? Is that okay? Well, here is your radial size, right? And then the force could be like what I guess you'd be like wrapped around it, right? That's something like that. There's your R cross up there. I guess that. You guys see the width of the handle would have something to do with the radial size for the torque, right? And making it longer doesn't really add torque in the turning direction like that. Okay. Different axes of rotation. Maybe we should put in the axis of rotation. Right? Um, for the screwdriver trying to turn this nut, here's the axis of rotation right here. Right? For the screwdriver, turn the screw. Here's the axis of rotation right here. Right? Different axes of rotation. Finn, the points. All right, last question for the win. A ring, a disc, a solid ball roll down a hill at the same time. Who reaches the bottom first? Ooh, one winner, the ball. All right. And why would it be the ball? Oh, because I gave you a hint in parentheses there, something to do with rotational inertia. Right? Now, in the premise, it says having equal masses. That's actually not really an important point, though. Right? Even if they were different masses, the answer would still be the same. Right? So, hey, that's this poster right here. Right? You guys remember roll race? Right? So, what have we got? I've got a surface with some friction on it. I'll call this like coefficient of static friction. Right? Static so that it's rolling without slipping. A lot of times, physics textbook will specify that. Right? Okay, so there's friction with one exception. Right? I have one frictionless lane. Right? That's just so I can send one air hockey puck down and I can just compare with all these other things. Right? So this frictionless surface air hockey puck is going to beat everything. Right? And then the static friction doesn't actually remove any energy from like the ball surface system or the ball earth system, right? But it does induce rolling, right? Which means that some energy goes in making it roll, right? Which means it's going to lose the race to this air hockey puck, right? But okay, now let's compare these four guys. Okay? So it has everything to do with how the mass is distributed, right? Again, if they were different radial sizes or different masses, that ends up canceling out, right? Not being important for their motion. Like if you had a marble next to a bowling ball, if they were both solid spheres, then ideally they would tie. Like they would both respawn at the same time, even though they're different masses, different radial size. Okay? But the bowling ball has its mass distributed closest to its center among these four objects. Next is the cylinder. Right? So that's this guy right here. Right? Then the spherical shell. That's what a basketball is, right? Like a spherical shell where all the mass is like on the outside. Okay? That has a lot of rotational inertia, like per unit mass. Okay? And then finally, this ring. Well, that's like as extreme as you can go, without like extending the mass like beyond the radius that's actually rolling about. I guess you could do that too, right? Yeah, so that's going to lose the race for like all these like conventional rolling objects. Like in fact, you know what? I got some other posters about this too. If you want to solve for exactly how fast is the ball going at the bottom of the incline, right? There's a couple ways you can solve it that I know of anyway. Right? And probably the easier way I think is with energy here. I do have another poster with the other answer. Okay? So the other solution. Okay? You could go through a free body diagram with torque. It's even skipped a few algebra steps here. This is kind of a complicated way to do it. You have to bring in parallel axis theorem, blah, 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 right? But you get some answer. But with energy, I think this is a more straightforward way to do it. Same answer, right? Same answer, right? So it's all potential energy at the top. And then the bottom, it's kinetic, but it's two kinds of kinetic. You've got the linear kinetic, pointed radar gun, there's 1/2 squared. There's also, oh, look, energy that goes into making it rotate, roll. There's 1/2 I omega squared, right? Now, this I and this M are related to each other. Some do with MR squared for basketball, like a spherical shell, it's 2/3 MR squared, right? So that's specific to basketball. Right? And then omega, well, that's like V over R, right? That's this right here, right? V divided by R is omega, how fast it's rolling. Right? So there's a connection there too. Okay. Right. And the solution you get, notice that the mass of the basketball is not part of the equation, right? And neither is the radial size of the basketball. That doesn't matter either, right? But it does matter that it's a spherical shell and all mass is like on the outside surface, right? That's what goes in this like 6 right here. Okay. I guess that. As for basketball, if it was like any other really shape, you have to like change this out, and the answer would change a little bit. Okay. Okay. All right, you guys get there? You also want to say about this roll race. Right, let's look at the roll race. Is what if you had an incline on the opposite side, or maybe there's like a smooth transition and there's an incline on the opposite side? Okay. What would this look like? Okay, so let's do that. Let's do an extension. See, it's like a half pipe type shape. Okay. So it could look like that. Okay. And let's have right. How about a bowling ball versus a basketball? I guess we'll do that. All right. Yeah. Okay. Bowling ball versus basketball. So here's a bowling ball. See if I can draw a basketball. There you go. Bowling ball, basketball. Okay. Okay. And you let those both go. Right. What would they look like? Now there is static friction, but let's say there's no kinetic friction, so there's no sliding. Right. What does this look like? Right. I'm going to exaggerate this a little bit, but here's what the bowling ball does. Zoop, 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 zoop. Here's what the basketball does. Woo, woo, woo. goes a bit slower, right? Okay, it's kind of exaggerated, but the idea is that uh, there's no energy that's leaving the system. So if there's no energy loss, they could do that for like 1,000 years. Right? That's right. Right. But yeah, the bowling ball would be going back and forth faster, and the basketball would just be that same motion but slower. Right. All right. Switch over to Kahoot. Let's see who won this thing. Who wins the Kahoot? With the bronze, Jake the dog. With the silver, Geo. And the gold, in for the win. The runners up, Paige and Caitlin. Good job. All right, so back over here. So we've got about 8 minutes of class left. Let's do a little bit of review. This rotational question. Take the last few minutes here. Um, how about what if you have a turntable? Let's get a turntable going. Let's turntable. Right, you guys remember working with those turntables, right? Gets spin about this central point right here, right? And let's say you give this a spin. How about counterclockwise to be the positive direction? I'll call it omega naught. Okay? And let's say there's some friction that slows to a stop. Right? So friction that slows to a stop. Ooh, okay. Let's make three kinematic graphs. Three graphs for kinematic motion. You guys remember X versus T, B versus T, A versus T? Right? You guys got your notes out, right? You guys got notes out? I'm going to walk around the room and see how many of you guys get this. So the rotational version of that is theta versus T, omega versus T, and alpha versus T. Okay. How about units? Let's put in units. What's the units for theta? What does theta represent? Angular displacement, like how far it's turned, right? And how can you measure how far something's turned? Can you make, okay, can I use this right here? Measure how many degrees? Okay. But what's the like more mathematically pure way to represent angles? Not degrees, but radians. Right? Maybe I'll call this like radians. Right? If I want to do any math with these kinematic expressions right here, I have to use radians for theta, right? Theta, angular displacement has to be in radians. Okay, so time could be in seconds. Ooh, omega. Well, I said omega naught, like initial angular velocity. That's what omega is, right? Angular velocity, right? And what's the unit for that? Radians per second. Okay, then time is still in seconds, right? And then alpha could be angular acceleration. Could that be radians per second per passing second? It's called radians per second squared. Right? Time is still in seconds. Right? So remember your scenario is turntable slows, I'll say uniformly to a stop. If I didn't say uniformly, you'd probably assume that anyway for this class. So right? Slows down at a constant rate. Okay. Slows to a stop. All right. All right. So I'm gonna walk around class and see who can draw this correctly in their notes. Who remembers how to do that? Yeah, then got who's gonna get these? Okay, see. So we guys get close, okay? All right. So we guys getting really one or two of them right, but yeah, I think Finn got all three. Right. So I usually start with the middle one and branch out. That's what I've been doing all semester. So just keep doing that. Okay. So if it slows uniformly to stop, and I gave it initial angular velocity omega naught, maybe that could be like this, right? This could be omega naught. It could be like some point, some radius per second. It slows to a stop. Hey, slows to a stop. Okay, so stop means it's not rotating. Does that mean zero angular velocity? Okay. Now, it takes time to get there because it's slowing down. Okay. As it slows down uniformly, that means it's slowing down at a constant rate. Right, so this middle graph, does that just kind of look like that right there? Right there? Okay. Okay. So remember, all three of these graphs are related to each other. Displacement versus time, velocity versus time, acceleration versus time. Okay? And this middle graph, velocity versus time, is probably the most information rich, right? It's one step away from displacement, one step away from acceleration, right? Is what property of this graph we just made? How about this? What does the slope represent? What does the slope represent? Angular acceleration. We can label that alpha if I wanted to, right? Okay. Now that slope, if you're walking left to right, you're walking downhill, right? Which means that the slope is what? Positive or negative? It's negative, and it's constant. Right? Constant because that word uniformly. That word uniformly goes hand in hand with it being a straight line, right? But for this class, you would probably assume that anyway. Right? Right. Anyway, what I'm trying to get at is this last graph: acceleration versus angular acceleration versus time. Could you guys just draw this right here? And I could label that like some value alpha, okay, which is the same thing as the slope. The slope of velocity versus time tells you the acceleration versus time. Oh, look, it's negative and it's constant, right? Negative constant. Well, very well constant. Right? Okay, and finally, displacement versus time. Well, I guess angular displacement versus time. Okay, this might be the trickiest one to figure out. Okay. Here, how about this? What property of omega versus t tells you theta versus t? How about the area under the curve, right? Right. Let's sort of like reconstruct this because I think some of you guys might remember like from scratch how to do this, or maybe some of you guys don't remember. So let's break this apart. Let's say it takes like 3 seconds to break to a stop. 1, 2, 3. You guys see 1, 2, 3 seconds, right? The area under the curve tells you the change in angular displacement, right? Like how far it's turned, right? Okay. And if you had forgotten that or didn't know, then remember you can always look at the units, and the units tell you something about properties of the graph. Radians per second, seconds. It's like if you divide those two, like rise over run, that's something to do with slope. That'd be radians per second per second. That's radians per second squared, but we already did that one. Okay? But if you multiply those two, as radians per second times seconds, does not leave you with radians, right? Radians, right? Which is an angular displacement, which might be a hint that the area under the curve tells you angular displacement. That area that I hatched during the first second, ooh, that's a lot of angular displacement. So if it started from 0.0, which I guess you wouldn't have to start from 0, but if I start from 0, then it acquires a lot of angular displacement during that first second. But look during the next second, it still picks up area, but not as much, which means it doesn't turn as far. So it's like a curve that's kind of bending downish. And then during the very last second, yeah, it picks up a tiny bit, but hardly any at all. So it's still like rotating, but it's like coming in to a stop. Doesn't that create this type curve right here? Right? Oh, and guys, what shape is that curve right there? What shape? Parabola. That's a parabola going on right there. Hey, you know what this looks a lot like? This reminds me of a car braking to a stop. Doesn't that look like a car braking to a stop? Right. Which would be a linear example. Right. Oh, you know what? I have a poster for what we just did. Hey, that's that poster right there, which is also hanging in my room. It's been there the whole time. Aha. There you go. Right, well, bell's about to ring, so let's end class right there.